In the Netherlands, a construction crane calamity.
I heard metal to metal. It was definitely shocking.
A potentially fatal flaw strikes an iconic San Francisco bridge.
If any one structural component fails, the entire bridge can go down.
In Louisiana, mystery as a massive whirlpool drains a lake.
It's the site of one of the greatest engineering catastrophes in this country.
And tragedy strikes a Florida beachside condo.
I was coming out and saw the condominium physically collapse right in front of me.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. Some with deadly consequences. These catastrophes are every engineer's worst nightmare. One basic rule of construction is to check and double-check your figures. Because when engineers miscalculate, the results can be catastrophic. Like this bridge project in the Netherlands that nearly crippled a town.
With this job, small mistakes led to a major catastrophe.
As a complex crane operation went drastically wrong.
I was, of course, very fearful. It was difficult to understand what did I see.
Every engineering student should look closely at this case. What went wrong here could so easily have been avoided.
The low-lying Netherlands are home to nearly 10,000 kilometers of rivers and canals, forming the densest network of inland waterways in Europe. The town of Alphen aan den Rijn lies at its heart. As local journalist Vera Vergunst explains.
The waterways here in Holland are very important to connect the whole country. So this one is the only one you can go from north to south, and it's used by cargo ships, sailing boats, pleasure boats, and the biggest yachts.
With so many waterways, bridges are a way of life.
So this bridge, the Queen Juliana Bridge, is the most important bridge in Alphen because it connects that side of the city to the other side, and it's the only bridge in the center you can pass by car.
It's not just about city traffic. Without this bridge, cargo and large pleasure boats wouldn't be able to take the scenic shortcut that this river offers.
About 20 times a day, traffic grinds to a halt as the Queen Juliana Bridge opens to allow larger vessels to pass through town. Back in 2010, the constant use had taken its toll on the steel, and the decision was made to replace the lifting span.
Now, this meant entire sections of the bridge would need to be lifted by crane and carried to the riverbank. The challenge was how to get the cranes close enough to the bridge.
With the banks cluttered with businesses and homes, engineers decided the best option was to work from the water. Amateur photographer and drone operator Dick van Smieren filmed the project from his canal-side balcony.
It was very spectacular to see in this area the pontoons with the big cranes on it. It was high, it was impressive.
The plan involved two massive cranes, one 700 tons, the other 400 tons, each mounted on a barge. This tandem lift would see the bridge deck lifted from a third barge. And once horizontal, slung between the cranes, the two barges would sail 100 meters to fit the bridge into the existing mounts.
I think a lot of people thought it was a pretty crazy idea to put cranes on pontoons, but I think here in Holland the engineers are like very innovative, and we trust them. So we were like, well, this will be okay.
Since I love filming and photographing, I took the drone and it showed, of course, the impressive perspective of the huge cranes and how those cranes were ready to pull the bridge and take it to its new place.
August the 3rd, 2015, lifting day. The town looked on as the cranes took the strain.
Actually, that day it looked normal, so impressive to see it.
At first, the crane stood perfectly balanced, almost as if frozen. But once the lift started, the picture changed dramatically.
But the first thing where it really was strange was when I heard metal to metal. You would not expect that in so careful operation. And then you could really see the bridge moving, touching the crane. It was definitely shocking. You see that collapse. Of course, you think there are victims. The first thing I did was calling ambulance.
Footage from a security camera reveals just how dangerous the situation was.
Four houses on the water collapsed, and the two other houses on the other side of the street also collapsed because the crane was so big. He destroyed all of the houses, and a lot of other houses were damaged by the accidents.
For the authorities, getting into the houses which the cranes had crashed onto was the priority.
Incredibly, despite 20 people being injured, no one was killed. With cars unable to cross the bridge and river traffic on hold, the authorities raced to get the bridge repaired and to determine exactly what had gone wrong. The town turned to engineering expert Jacques Aerts to analyze the accident. And Jacques turned to Dick's footage.
The drone film from Dick was really useful because it was give a nice overview from all different angles. It really helped to figure out what they were doing on the job site. We started with the data from the lifting plan. After that, we checked condition at site was exactly as what they had planned.
The key problem was in the balance calculations for the delicate and highly complex lift operation.
The preparation, it's quite a lot of engineering to be done, especially in this case with two barges, or actually three barges, and one barge with a load as well. Two cranes, wind, current, maybe even waves. So it's really complex, so you have to do really proper engineering in advance to determine if it's feasible or not.
Major discrepancies between the theory and reality quickly emerged, based on miscalculations of the rig's stability.
Especially on the small barge, there was a lot of additional equipment and material. Also, the ballast condition of the barge was not according to the plan, and all these changes reduces the stability.
The inherent instability of the barge with the smaller crane caused it to list to one side. The excessive sideways forces buckled the crane's mast, which toppled, pulling the bridge deck and the larger crane with it.
They have done some preliminary checks in the beginning of the project, but during the engineering, a lot of Small things have changed. Small errors or changes in the engineering can lead to major accidents.
Leaving the town without its only vehicle crossing wasn't an option. So the authorities planned a second lift operation. This time, nothing could go wrong.
For the second attempt, a bespoke floating crane was used. It's an expensive option, but one which hugely reduced the risk of a disaster.
The bridge was finally operational nearly a year late and thousands of euros over budget. But for residents, the reopening was a huge relief.
The town was, I think, very happy when the bridge was finally reopened, because it was really missing in the city center.
When engineers push boundaries, sometimes the danger comes from the outside. But other times, even the mightiest of structures can be threatened from the inside. Like this construction calamity in California, with an engineering marvel that came dangerously close to catastrophe.
One of America's most iconic bridges could have been one snap away from collapse.
A cutting-edge design that could have turned into an epic engineering disaster.
The design defect could have brought the whole thing crashing down.
San Francisco is home to some of the West Coast's most iconic postcard views.
I love San Francisco. It looks stunning, it has culture, amazing architecture, and of course, an endless, beautiful waterfront. In fact, the city is surrounded on 3 sides by water.
All this water means one thing: bridges. The Golden Gate is the city's most famous bridge. But there's another here that's a far greater feat of engineering. The San Francisco-Oakland Bay Bridge, better known simply as the Bay Bridge. It's the city's most important crossing, as engineer Andrew Freemier explains.
The San Francisco-Oakland Bay Bridge by itself is the biggest workhorse of all of the 8 crossings that are in the San Francisco Bay Area. And so on an average day, hundreds of thousands of people commute across that bridge. And it's very important for the community and for the economy for that bridge to stay open and operational.
When it was built in the 1930s, the Bay Bridge was the longest and most expensive bridge in the world. But in 2013, a radical, unique middle section opened. Although just a fraction of the length, it alone was California's most expensive public works project ever. With an iconic single tower topping 160 meters and a span of more than 380 meters, this is the longest self-anchored suspension bridge in the world. Bridge engineer Brian Maroney helped build this epic structure.
Here we are at the top of the tower of the self-anchored suspension bridge. If you look to the west, you see the beautiful skyline of San Francisco. And as a bridge engineer, looking at the on and off ramps and the Bay Bridge going in and out of Yerba Buena Island Tunnel, very exciting.
It's not just the view that sets this bridge apart from its peers, but the way that it works. Unlike a conventional suspension bridge, which has 2 cables anchoring it to each side of the crossing, a self-anchored suspension bridge is entirely supported by a single cable. Here, it forms an open-ended figure of 8, supported by the single 160-meter tower.
One of the most challenging parts of this entire bridge is the cabling system of the self-anchored suspension bridge. The anchorage is on the east end. It comes up the top of the tower, continuously goes around, wraps around, comes back up to the top of the tower, and then comes back to the other side of the east anchorage. The entire length is over a mile, so it's a long cable.
The cable consists of 17,000 individual wires bundled together and anchored at the Oakland end of the bridge.
We're here at the east end of the self-anchored suspension bridge, deep within, inside the superstructure. This is the splay chamber. This is basically where all of the cables come down and anchor. So the parallel wire strands, each one of them, even though it's approximately about a meter diameter main cable up on the bridge, they splay out here in the splay chamber, and you see all these parallel wire strands, and they splay out into smaller groups of wires. They get cast into what we call a socket. Then the socket is screwed into a rod, and the rod goes all the way back against an anchorage. That's a heavily, heavily reinforced steel wall, and it's screwed in tight.
This unique bridge wasn't just built to break records. The radical design is to combat something San Francisco is famous for: earthquakes. Journalist Charles Pillar explains.
We live in one of the most earthquake-prone environments in the world. There's two major earthquake faults that are adjacent to the Bay Bridge and affect the Bay Area more generally: the Hayward Fault, which is just in the East Bay Hills, and the San Andreas Fault, which is closer to the coast. Both of these are faults that have had major earthquakes in the past, and in particular, the Hayward Fault is thought to be likely to have a major earthquake, possibly quite soon.
In 1989, the San Andreas Fault triggered the massive Loma Prieta earthquake, and a section of the Old Bay Bridge slid from its supports. Engineers realized the entire section was vulnerable because it was built on soft mud. So, when the new span was built, the solution was to have a single tower standing on the only solid rock in the area.
This self-anchoring method means the cables are attached to the end of the deck rather than the ground, which means the structure has much more flexibility in an earthquake.
The self-anchoring section of the Bay Bridge was built to survive an 8.5 magnitude earthquake. But something significantly smaller almost sent it crashing into the bay. In the 1989 earthquake, the section of road deck that collapsed had been shaken from its supports. To prevent that from happening with the new bridge, the decks are joined to the legs using connections called shear keys. Engineer Brian Maroney explains.
Shear keys are devices that hold on either side of the bearing to keep the superstructure from sliding.
The Bay Bridge shear keys have two parts: a 3-meter square base bolted to the eastern pier by steel rods over 7 centimeters wide. This links to a second plate on the road deck above, allowing movement much like a trailer ball hitch. As well as coping with everyday loads, if an earthquake hits, the design allows the two parts to shake independently without causing damage. Although engineers didn't know it, long before the bridge was complete, trouble was brewing in these crucial connections.
The shear key rods were concreted in place in 2008, but the giant nuts couldn't be fully tightened until the bridge above was constructed too. This was a massive project, so the bolts sat there untightened for 5 years.
And when the nuts were finally tightened, 32 of the steel anchor rods fractured immediately. This massive fail left the bridge vulnerable.
Had an earthquake hit, the very elements designed to protect it could have led to its ultimate destruction.
Metallurgical engineer Lisa Fulton investigated this potentially catastrophic problem.
This bridge is what is known as a fracture-critical bridge, which means that any one structural component, if one fails, the entire bridge can go down.
Despite the structure's super size, the failure was caused by a microscopic problem known as hydrogen embrittlement. It's a type of corrosion where hydrogen atoms diffuse into a metal structure. As the atoms slowly recombine into hydrogen molecules, they form a gas that creates pressure inside the metal. Ultimately, the rods become brittle.
hydrogen enters the steel and has an embrittling effect on the steel. So embrittlement is when something breaks without absorbing a lot of energy.
Even under very little pressure, hydrogen embrittlement can make steel snap. With a massive force, like the shaking of an earthquake, any brittle steel would be a serious risk.
With the discovery that the shear key rods had failed, people were obviously worried that other steel bolts and even the main cables themselves might be at risk.
This bridge is an amazingly unique creature. The question is whether this self-anchored span, this unique design that is replicated at this scale nowhere in the world, whether it can withstand the strongest level of quake that could occur on the Hayward or San Andreas Fault. And Caltrans says yes. We've done our computer modeling and we feel confident of it. Of course, on the other side are many engineers who doubt it and who question it.
If the officials say the bridge is safe, you just have to trust them. But had the main cable been vulnerable, with this type of bridge, it couldn't be replaced. There would have been no choice but to tear the whole thing down and start over.
This is the cable that holds up the suspension span. It's crucial that there not be any corrosion on it.
What was not in doubt was that 32 of the shear key rods had fractured. If a quake hit, no one could be sure what would happen to the other rods, and engineers didn't want to find out. The rods couldn't be replaced, so they worked round the clock on an alternative solution to hold the shear key in place.
What we did is we created a saddle, just like a saddle that you put on the back of a horse, and then we strapped or pulled down, cinched down that steel saddle, and then pre-stressed it and tightened it.
A pair of steel clamps called saddles were fitted over the sides of the shear key, with multiple steel rods and cables holding them in place, effectively strapping the shear key to the bridge leg. Whatever happens to the rods, the shear key isn't going anywhere. Finally, in 2013, the revolutionary new eastern span of the San Francisco-Oakland Bay Bridge opened to traffic. It was 10 years behind schedule and billions of dollars over budget, but San Francisco had added another striking bridge to its collection.
This ended up being the most expensive bridge ever built in America, but it could have been one of their costliest construction catastrophes.
When engineering goes wrong, the cause of the calamity can be huge and obvious for all to see. But sometimes the simplest mistakes can have devastating consequences. Like this mystery in Louisiana and a massive lake that vanished.
A tiny miscalculation changed the entire landscape forever.
Once this epic engineering fail started, there was no stopping it.
This catastrophe quickly spiraled out of control.
It's the site of one of the greatest engineering catastrophes in this country.
Louisiana, home to the Big Easy and endless bayous, where the mighty Mississippi River meets the ocean.
When I think of Louisiana, I think of swamps and lots of water. There's the long coast beside the Gulf of Mexico. It has vast bayous threading through the Mississippi Delta and endless lakes in between.
For thousands of years, the river has dumped layer upon layer of sediment to create a vast flat landscape. Geologist Tim Dukes has been studying the ground here for decades.
We're located in what is called the Gulf Coast area, the coastal plain, generally pretty flat.
Although the state is mainly flat, geologists like Tim have found the occasional mound that hints at something precious lurking beneath the surface.
These places are irregularities in that because they're salt domes and topographically higher, significantly higher. There are literally hundreds of these salt domes that are found in Louisiana and thousands that are found in the Gulf Coast. around the edges of these, there are a lot of areas where drilling for oil and gas can take place, and it's been pretty prolific.
Oil and gas have a dirty reputation, but they're both completely natural. Basically, the remains of billions of tiny plant and animal plankton that have been pressure cooked deep beneath the surface. The resulting stew is oil and gas. Because of the way they were formed under the ocean, oil, gas, and ancient beds of sea salt are often found together.
Over millions of years, salt forces its way up from deep in the Earth's crust towards the surface and forms salt domes. These domes create natural underground pockets that trap the oil and gas that formed below them.
In the 1970s, prospectors were drawn to a salt dome on the western edge of the Mississippi Delta, the so-called Jefferson Island, on the banks of Lake Peigneur. Tim was here in 1980 when engineers were searching for oil.
We're located on the shores of Lake Peigneur. There was a drilling rig that was located out more or less in the center of the lake, and they were drilling supposedly around the edges of this salt dome.
Michael Richards Sr. was working on Jefferson Island at the time.
When I came to work here in 1969, we used to mow grass between here and the pilings. There was a grove of pine trees right here.
On November the 20th, 1980, as the rig drilled into the lakebed, the drill jammed solid, and Michael grabbed his film camera.
Soon after the drill bit became stuck, the whole rig started to tilt. The rig workers knew that something was seriously wrong and evacuated the rig. After they reached the shore, it soon became clear they'd had a lucky escape.
The rig quickly disappeared through the lakebed, and a giant whirlpool formed where it had stood just minutes earlier.
Once a whirlpool had formed, the spinning water rapidly eroded a hole in the bottom of the lake. Although small, it was big enough to suck in the whole lake.
Michael continued to film.
We were standing on the porch on the second floor of this house that you see here that's sunk about 30 feet, looking down on the lake and watching the barges rolling around, a tremendous vortex. And then at one time there were 3 different vortices, each one turning and swirling.
The lake was rapidly being sucked underground, but the force of the whirlpool soon started dragging more than just the water within. In addition to the water, about 65 acres of Jefferson Island also disappeared through the lakebed.
The land in the bottom of the lake was peeling off in great layers like a cake. And behind us, the water was liquefying the soil. And in that direction where there were trees, the trees were holding, the roots of the trees were holding the soil. So the soil slipped and the trees laid down. You can still see the tops of some of those trees today.
Michael discovered that filming on location could prove deadly.
Sheriff's Department came in and told us it's time to go. So we left. And not long after that, the house and all this land slipped in. The progress started moving in this direction.
With Lake Peigneur no longer a lake and a huge part of Jefferson Island missing, everyone was left asking, where on earth had it all gone?
Jefferson Island was the surface evidence of a salt dome, which is why rig workers were looking for oil trapped beneath the salt. But as they knew all along, there was also a massive salt mine being excavated beneath the island. In fact, it was about the size of a skyscraper.
The salt mine was at considerable depth, several hundreds of feet. I think the deepest level was down to 900 feet, and it was an active mine at the time. They were pulling out salt. This is an example of what they were after.
It turns out that instead of discovering oil, the rig had inadvertently drilled through the roof of the salt mine.
Because of the safety conditions that were present and the procedures that they had established, all of the miners were able to get out without anybody being injured or killed.
This explained where all the water had gone, but not why the rig had drilled into the salt mine in the first place. After all, it had been known about for 60 years. According to geoengineer David Wilshaw, it was all because of a very simple but catastrophic mistake.
What happened is basically they got their calculations wrong about where to put the drill rig and where to drill the oil exploration well. They were out by a few hundred feet. So they never anticipated drilling into the salt. They were looking for the oil and gas deposits that sit around the salt dome.
When deciding where to drill, the engineers used a method called triangulation. Basically, angles from two or more fixed points are used to locate another point. The problem was they made a mistake in their calculations and drilled in the wrong place.
That small error might have made the difference between finding oil and this massive disaster. Thanks to modern technology, it's a mistake that would be unlikely to happen ever again.
Today we have GPS. Back in 1980, it wasn't so simple. They didn't have the satellites that we use. I mean, we could probably avoid doing that just using our phone today, but you can't turn back the clock. You can't see what the technology they had there. Would it have been avoidable if they'd had more, obviously precise instruments? I'm sure it would have been.
This minor miscalculation not only wrecked an oil rig, it also brought a watery end to a fully functioning salt mine. But it was an unexpected new beginning for Lake Peigneur.
The suction created by the whirlpool was so strong, the canal that used to flow from the lake into the Gulf of Mexico reversed, basically refilling Lake Peigneur with seawater.
After a considerable amount of time, the waters came back up, all the barges popped back to the surface, and the lake kind of achieved its present level.
Lake Peigneur is now 20 times deeper, and Jefferson Island is significantly smaller.
All of this land slipped in. It's unbelievable, the magnitude of this catastrophe.
With this blunder, there really was no solution. The disaster permanently changed the landscape. The sea refilled the lake and the mine was lost. It just goes to show that when it comes to engineering, getting your calculations correct really is essential.
Some engineering fails lurk hidden for years after the construction crews have left the site. But with others, the fail strikes before the job is done. Like this condominium in Florida, and an engineering error with truly tragic consequences.
This real-life disaster was set in motion right from the drawing board.
Saw it actually physically collapse right in front of me, and you just saw a huge, huge ball of dust.
A fatal failure that forced the engineering industry to re-examine the rule book. Florida's seafront city of Cocoa Beach is sandwiched between the Atlantic Ocean and the Banana River. Famed for its long sandy beaches and one of the world's largest surf shops, this town actually owes its existence to America's space program. Local Florida engineer Julie Keller explains.
Close by to this area, we have the Kennedy Space Center, which brings in a lot of science and engineering people and needs the availability to house them.
In the 1980s, with NASA's shuttle program in full swing, Cocoa Beach was busy building.
There were building booms back in the 80s and the 90s, and anytime you have a building boom, there's always a need for construction to be done faster and at a quicker rate.
In December 1980, to keep up with demand, work started on a new 5-story condo, the Harbour Quay. Although it was never completed, it would be built like many other condos across the country.
We are headed to the site where the original Harbour Quay condo was supposed to be built. This would have been a prime piece of real estate to put a 5-story condo on. What we have here is an example of what the Harbor Quay could have looked like. So this building is typical of the area. It's a condo that's 5 stories high.
Each level would be made up of large flat slabs, held up by columns. To maximize internal space, there would be no additional horizontal beams. The slabs would be strong enough to support themselves.
Concrete is great for construction. It's very strong as a supporting block, but when it's used as a floor or roof panel, it has to be self-supporting. That calls for serious reinforcement.
Setting steel bars inside concrete is key to structural strength. The concrete resists squeezing or compression, while the steel resists bending or tension. But to work properly, the exact height of the bars is critical. With Harbor Quay, the plan was to use a process called reinforcement chair design.
So what we have here is an example of what you would see on a typical construction site where the slab is being poured. And you would have these form boards, so it would make the mold of where the concrete's gonna go. The location of this bar is critical in the placement of the slab because all the calculations are based off of where this bar is.
The idea with the chair system is to hold the rebar at exactly the right height. If those measurements are out by even a couple of inches or centimeters, the whole thing can come crashing down.
3 months into the project, on March the 27th, 1981, the construction team was pouring concrete to create the roof 5 stories up. But shortly after 3 p.m, the build went drastically wrong. Kent Fay was 20 at the time, working as a lifeguard just across the street.
On that day, I was leaving work to head over to have my paycheck cashed over at the local bank. And as I was exiting, was coming out and saw the condominium, Harbor Quay condos that they were building, saw it actually physically collapse right in front of me. And you just saw a huge, huge ball of dust.
The collapse happened so fast that there was no warning for workers.
I quickly ran over there. I got up on the scene. I was dealing with people that were severely, severely injured. There was a young man on the ground that was actually in shock. They went and got him up and had him help me start attending to people that were injured.
Residents and construction workers rushed to the scene to join the rescue mission, quickly followed by airmen from the nearby Patrick Air Force Base. 23 workers were injured, but despite the rescuers' best efforts, tragically, 11 died. The disaster left the community reeling and demanding answers. The obvious question was why had the Harbor Quay condo collapsed without warning? Within an hour, a team from OSHA, the Occupational Safety and Health Administration, was on site to investigate.
According to official reports on the accident, investigators found clear evidence in the wreckage of what had gone wrong.
The investigation discovered a number of failures, most notably in the reinforcement chair design. Engineer Julie Keller explains.
The reason that this is critical on this particular condo is that the steel not being in the right location was found to be because these chairs were not the right size. The chairs were not the right size because the engineer signed off on the shop drawings showing the chairs in the incorrect size. And that led to the steel being under so much stress that every time you put another floor on it, there was additional stress on the condo. So it led to a brittle failure.
Brittle failure is when concrete cracks suddenly and without warning. As structural engineer R.N. Sailapan demonstrates.
In this test, we are going to be determining the flexural strength, the bending strength of concrete. Right now, we have applied a load of over 5,500 pounds. Now it's way over 6,500. These concrete specimens are expected to break with a bending strength of about 500 or 600 psi. As you can see, this beam was tested to failure. However, this is not how it is in the field. In the field, when we're actually constructing a building, you would have reinforcing steel in there, which greatly enhances its capacity.
But the brittle failure in the concrete wasn't just the result of the steel being positioned incorrectly. The original design didn't call for thick enough concrete in the first place.
Even though this bar should have been down here, the slab was designed to be 8 inches thick. So that's what the engineer had done in design. But the American Concrete Institute has a code which says that a flat slab supported on just columns should be 11 inches thick. So the distance between the compression and where this bar should have been, that critical number that was in the calculation, should have actually added 3 inches, not just the inch that was lost due to the chair size.
Typically, in order to increase the bending capacity of beams and slabs, the steel is placed in the lower portion of the cross-section. But in Cocoa Beach, it was placed almost at the midpoint, which effectively does not contribute to increasing its bending capacity, because as you can imagine, when this beam bends this way, the bottom is in tension and the top is in compression.
Concrete works really well in compression. It does not work well in tension. A teacher a long time ago told me that if you join your hands together, you can see the example from if you push on your hands, you see your skin wrinkles on top, and that's compression. So you can see that happening, and then you look under your hands and you can see the skin stretching, and that's tension. And that's where the cracking forms, and that's why this needs to be in the correct location in order to do its job.
It seems that there were multiple miscalculations. The chair size was out, the thickness of the concrete was wrong, and the calculations in the original drawings were based on rebar that was 1/3 stronger than the steel used in construction.
The calculations were wrong on every floor, so as each was being completed, the problem was being compounded. It was just getting worse and worse.
Ultimately, these factors combined as the 5th floor was being poured, leading to a failure known as punching shear.
With the rebar set too high, the bottom of the panels were being overstressed. When the concrete fouled, the panels fell, but in effect, it was the support columns punching through the concrete.
This type of failure happens in reinforced concrete slab structures. Where the columns support the slabs, they're subjected to very high forces. In this case, the slabs failed at these crucial points, and with no support, the structure collapsed.
They continued to build, and then when they put the 5th floor on there, it just failed suddenly.
There were mistakes at every stage, but by getting the numbers wrong at the design stage, this project was doomed from the start.
Although it was too late for the workers who lost their lives, the Harbour Quay condo collapse led to more rigorous enforcement of engineering and construction codes in Florida and across the United States.
It's critical that engineers learn from tragedies like this to help prevent anything like it from happening again.